The next usage of groundwater or of geothermal water that I want to talk about is kind of what I think about as a no-heat geothermal system. So a no-heat geothermal system is exactly that, right? It's using geothermal energy, but it's not geothermal energy gained from the earth, right? So in all of these other examples, we've seen places where there's concentrated heat inside of the earth, related to kind of deep inside of the earth, right, as that heat gets conducted and convected up through the earth. In this case, we actually use heat from the sun. We've got the sun, our favorite guy, a little sun up here. We can even put a smile on him. That sun warms the surface of the earth up with solar radiation, right? Remember, radiation traveling through space. So the top of the earth, it gets warmed up. And obviously in the summer, it's warmer. In the winter, it's colder. And so if you were to put a temperature probe, 6 inches down in the soil, you'd see the soil is warm in the summer, cold in the winter, right? So you'd see, if you looked at all the years, you'd see this kind of oscillating pattern, right? High and low, high and low. But if you think about that oscillating pattern, the further down you go in the earth, the more that kind of annual change is reduced. So once you get to about 10 to 12 feet down, the temperature in the soil at that point, the temperature in the earth at that depth doesn't change. It actually remains stable. And we actually use that to figure out what we call ambient air temperature. Like, what's the average temperature for the area? The ground actually averages it out for us. And when we start looking at the average kind of ground temperature, and this is also the temperature of groundwater, it doesn't vary very much kind of within the United States. Generally, 53 degrees Fahrenheit to maybe 56, kind of within that range. Warmer places have slightly warmer, colder places have slightly colder. But it's all generally in the low 50s. A good average would be to say 54 degrees. So to take advantage of that, we can think about, down here, we always have water that's at 54 degrees, or we have soil temperature that's at 54 degrees. And if we were to install a building, what we could do is we could hire our friend with an excavator or a backhoe, dig a hole, it's the type of thing you could do with new construction, and in that hole we could bury something that looks pretty much like sprinkler distribution line, just a whole bunch of pipes, right? Just coils, and water's going to flow through all of them. And we'll kind of continue that. Let's say that goes up to our building here, and it's got an in and an out, just like we've seen in the past. We then fill our earth in here, and at this point, now we have what some people call a heat coil. So you wouldn't notice any difference here on the surface of the earth, especially in one of the videos you see if you put a parking lot there. And what happens is if you pump water through this system, that water is going to come out of the system at 54 degrees. And it turns out this is useful in 2 different ways. So in the winter, you can actually just take the heat out of the ground and bring it into your house, run some air over it, and you have 54 degree air, you have 54 degree temperature in your house, and that significantly reduces the amount of energy that you need to bring your house up to a comfortable, let's say 70 or 72 degrees. So it kind of takes the bottom out of the energy that you're spending to warm your house in the winter. But in the summer, it runs the opposite way. So again, this temperature doesn't change over the course of the year. So if you have, let's say it's 100 degrees in your house, hopefully that's not the case. That sounds terrible. We're running basically a coil of cold water through the house, and it's absorbing that temperature and distributing that temperature back into the earth. And so in the summer, it will actually function as an air conditioner. This is not new technology. Back, kind of in the olden days, you could build a house underground, or you could excavate something, and at depth, the temperature stays much more reasonable, right? Cool in the summer and warmer in the winter. So There's a couple of different terms that we use for this. Geothermal heat loop. In some cases, some people refer to this as a geothermal heat pump. But really, in my opinion, the use of geothermal here is a little bit of a misnomer, right? Because this isn't heat from the earth. This is heat temporarily stored in the earth from incoming solar radiation. And you can even kind of think back to, we were starting to talk about the greenhouse effect and how, the earth stores energy from the sun. That's what we're taking advantage of here. So yes, you're getting the heat out of the earth, but the source of the heat is the sun rather than kind of radioactive decay that's happening within the earth itself. With geothermal politics, or again, in my mind, the charts and graphs section, we're not actually going to talk about that much. It's not enough for its own video, so I'm just going to tack it on the end of the no temperature geothermal section. And really what I wanted to talk about was places that are using geothermal. So we can kind of reflect quickly on this diagram that shows geothermal potential within the US, right? Obviously out west, where there's more recent volcanic activity, intrusive igneous activity, stuff going on inside of the earth. Also, the earth is much more fractured, kind of faults and fractures, so there's more flow paths for groundwater. Those places have a much higher potential. Reflecting back to that past section, the no temperature, that's something you could do anywhere. It's actually probably more closely related to solar, but you can even do it in Wisconsin. Right? That's not related to this. But when we look at states that are producing electricity or using, this doesn't include the kind of Boise geothermal system, the direct use or the low temperature. But if you look at places that are actually generating electricity, you can see they're all out west. California is number one. We talked about the Geysers geothermal plant near Santa Rosa, north of San Francisco. And that is a huge power plant. And actually, kind of up the California coast, there's a bunch more smaller ones as well. You can see Idaho, we make the list, right? We don't often make these kinds of lists, but we have geothermal heat in Idaho. So I mentioned the Raft River complex, southeastern Idaho, out near City of Rocks. But there's more potential. And so actually, if we kind of zap to this next diagram, you can see basically the same states show up. You can see shown in white, that's the current number in megawatt hours. That's the current amount of power that's generated in each of these states. We're at currently 18 megawatts. You can see Alaska is a pretty small number. It's actually a decimal, not even one full megawatt. But more interestingly, is actually the number that's shown in yellow. And so this is future and kind of planned install of more capacity for generating electricity. And so the same company that's operating the program out in Vail, Oregon, has more stuff planned in Idaho. You can see we're slatted for an increase of 75 megawatts to bring our total up closer to 100 in the low 90s. So you can kind of do the math there. When we look at California, you can see that they're really leading the way in geothermal electrical generation. Nevada does a pretty good job. Oregon is on track to double what they have, right? So they have 35, and they're going to add an additional 35. I think there's another plant going in near Vail. New Mexico and Colorado's making the list, right? So they're going to be investing in some geothermal electrical work as well, or electrical power generation as well. So the real limiting factor with geothermal is not cost. It's not cheap, but it's not incredibly expensive. It's carbon neutral. It doesn't kind of involve a lot of chemicals. It's fairly benign when we think about it as a power source. But really, the limitation is the heat, right? It's not the kind of thing where we can just start installing everywhere. We have kind of a geologic condition that has to be met for us to be able to generate that power. So it's not something we see scattered across the country, but it does make sense to increase what we do have, right? And when we start looking at what the power portfolio will look like in the future, we've talked about things like nuclear, right? You can start putting in nuclear power plants. Well, that still has some problems, right? We talked about nuclear has a lot of upside, but the downside is cost, is safety, is radioactive waste. But if you look at increasing our capacity for geothermal, it seems like a no-brainer, right? And that is something that we're doing. Okay, so that's going to finish us up for geothermal. I do want to kind of loop through, because this is now the end of our energy section of the class. I want to take a quick run through some energy types, kind of see where that stuff's distributed, and then we'll go ahead and dive into the next portion of the class, which is going to be metals, right? Thinking, don't forget, this is Earth's natural resources, which is not just energy, although energy is a big part of it. Okay, see you in the next video.